Oh, so let's talk continuity. Okay, so the second 1.4 assignment, we'll kind of give you the rest of the stuff you need to wrap up the 1.4 assignments. So let's talk about continuity. State the intervals over which this function is continuous. Okay. Talk to me.
Where x stops where x equals 0 and x equals -2.
Okay, and the reason being that those are the zeros of the denominator. Right?
Yeah.
Can't, any place except where we're going to have to divide by 0. So all we have to do is look at the denominator and see that because x squared plus 2x is in the denominator, we just solved that equation, that non-equation. So factor out an x, and we get the solutions, what? X cannot equal 0, and x cannot equal -2. Okay? So then state the intervals over which this function is continuous. So if we had to state the intervals where it is continuous, how would we maybe do that? Something like that? Okay. I like this. Just separate them with commas. When you separate the intervals with commas. Okay, so remind me though, we talked about, it's been a little while. Last week we talked about what it means to be continuous. So let's quickly review. What are the 3 criteria for a function to be continuous at a point C? What has to be true? Okay, first step is it has to be defined, right? F of C must exist. What next? Okay, the limit must exist. Good. Two-sided limit must exist. So the limit of f of x as x approaches c. When we say limit, that implies two-sided limit. Must exist. Good. Step 2. And then the third criterion. Good. Those have to be equal. Good. And then if that's true, the function is guaranteed to be continuous at that point. So what about these intervals here where the function is continuous? These are open intervals. Okay, so what does that imply about that point continuity? Like let's take this middle interval, and the interval where x is greater than -2 and less than 0, the function is continuous. What does that imply? How does that relate to the point continuity?
You can draw a line from a point close to -2 on the side greater than -2 to a point close to 0 that's slightly less.
Okay, but how does that, so how do we, that's true, but how do we relate that? You just gave me the 3 criteria for point continuity, right? And then if we can go back, and it's not very far back, I don't think. There it is, right? There's the function's continuous at a point. They called it point A, if and only if these 3 criteria are met at that point. Well, how do we extend that to continuity on an open interval? What must be true for every point on that open interval then? Well, all that stuff, right? So if we could say that we could say then for our example, if we want to relate those two things, let's just take this middle interval for example. For every point on the open interval, x is greater than -2 and less than 0, any point on that interval would meet those 3 criteria for point continuity, right? Okay, and notice that this is an open interval though, we're not including the endpoints. So now we're just in between those endpoints. And if we look at a graph of the function, let's just do that real quick. What was it was x plus 2,
X minus 1. X minus 1.
x squared plus 2x.
Yes.
Whoops. Okay, so there's
Plus 2x.
Oh, 2x. Okay, that makes it a little better. Okay, so we can see here that we've got some kind of crazy stuff going on. We've got some vertical asymptote here at -2. We got a vertical asymptote at 0. But on any interval in between those, we should be able to put our pen down on the board and graph this thing, right? Okay, it's a little bit hard to do because as I move to the right along this first subinterval, I gotta go down infinitely far to do it. But there's no point that I couldn't pick, there's no value of x less than -2 where I couldn't put my pen down on the board and make a continuous trace of that function. Agreed? So it's kind of a stretch. I mean, if we're going to talk, sometimes you have to exercise your imagination a little bit in calculus. It's a good working definition to think about continuities, being able to graph something without picking your pen off the board. It may be impossible to do with limited time, but I could, if I had enough time. There's no point that I couldn't reach by going to the left along this interval or getting increasingly close to -2 along this interval. I'd have to have an infinite ink supply in my pen. Does that make sense, though? But I would, in order to get from a point on this subinterval to this one, I do have to pick my pen up to jump over that asymptote, right? Okay, what if, arbitrarily here, what if, or hypothetically, what if this one had gone like this instead? What if this guy had gone up to infinity like that? Would those be continuous? No, they wouldn't be continuous because there's still no way to ever bridge that vertical asymptote without picking your pen up. Because you can't ever get to the top, right? Okay, does that make sense? You see how that's consistent with our working definition, our graphical definition? Okay? Okay, next example. How about this one? We always want to start off with the domain, don't we? And we did last example too. Right. Last example, you guys told me immediately, I think I erased it, but you told me right away that 0 and -2 had to be excluded. Those were the excluded values. And what you, in essence, told me is the domain is all values of x except those. Same approach here. What's the domain going to be?
X is less than or equal to 2.
Okay, now, how are we getting to that?
Because you can't square root a negative number, so x squared cannot be greater than 4.
So the red flag here is inside the radical, right? We've got a square root. And so we know that the argument of a square root has to be non-negative. So whatever's in the red bubble has to be greater than or equal to 0. Well, what's in the bubble is a 4 minus x squared. There's a number of ways to do this algebra. I could add the x squared to this side. Probably the thing let's just subtract 4. So I'm going to get -x squared is greater than or equal to -4, multiply by -1, so x squared is less than or equal to 4. And then here's where now if I square root, what do I get? You remember how this works? We can fill in, we're going to get a plus or minus, but we're not solving an equation this time. If I square root both sides, it's true that the square root of x squared has to be less than or equal to the square root of 4. But what is the square root of x squared? Absolute value of x, right? So the absolute value of x is less than or equal to 2, which tells us then that statement's easy to deal with. If we have an absolute value inequality like that, I know that if I'm taking an absolute value that's less than or equal to a number, it's going to be trapped in between the positive and negative values, right? So that tells us x is greater than or equal to -2 and less than or equal to +2. Okay? So that is the interval where it's continuous, right? That's the domain of the function. But what about the endpoints? It makes sense graphically, doesn't it? If I graph this one, if I graph this function, x squared minus 4? Is that right?
4 minus 4x squared.
Whoops. There it is. Where can I put my pen down?
Any point between 2 and 2.
No, including -2 and 2, right? So I should be able to put my pen down right there, and I can trace this whole thing all the way up to and including +2, right? So that interval really is what we said it was. Oops. It's this, right? If we write it in interval notation. That's a closed interval. Okay. So how do we relate that to, once again, the notion of continuity at a point? For every point on this interval, we ought to be able to establish that it meets all 3 criteria for point continuity, right? You see there's a difference though. What's the big difference between this example, raise your hand, between this example and the last one? Kurt, you see any difference there between this one and, I got rid of the graph already, but between that one and that guy? Say it again.
There's only one.
There's only one, okay, there's one subinterval. Sure. Okay, yes, Jill.
The one that we were just working on was on a closed interval.
Oh, it's a closed interval. Yeah. Now it's a little different, isn't it? On this one right here, we know that for any point between -2 and 0, I can strictly apply the criteria for point continuity. Pick a point that's on that interval somewhere. Can I pick -2? I can't, because we're not including the endpoint. So I can get arbitrarily close to -2, like I could pick -2.000001 if I want to, but there's still going to be an infinite number of points that are between that point and -2, right? So I can always approach that point from both sides. In each of these cases, any point that I choose, I can always talk about a 2-sided limit, because an ant can take little itty-bitty steps and walk towards it from both sides, right? You see what I'm saying? That's different than this guy though, right? This guy here, we're on a closed interval, so when I'm actually standing at x equals -2, there is no point less than that. That is the endpoint, right? So what must we do at those endpoints then? The criteria, the way we've defined it, don't strictly apply. If we go back and look at those 3 criteria that we've been using right there, what do you think we must have to do if we're talking about the endpoints of a closed interval? We got to be a little bit more relaxed about our definition of a limit.
Just has to be a one side.
Yeah. Really, only the one-sided limit could apply in that situation, right? You can't approach it from the other side because it's already an endpoint, okay? So if we want to look at this example right here, all we got to do is say, okay, we want to talk about continuity on a closed interval. Let's just be more general and say from A to B instead of from -2 to 2. What are the criteria for continuity on a closed interval? Well, for one thing, on the open interval from A to B, we'll meet our 3 criteria. F of C exists, the limit of f of x as x approaches C exists, and the limit of f of x as x approaches C is equal to f of C. And we're assuming C is on this interval, let's say, on our closed interval somewhere. Now we're saying it's on the open interval. So we're saying for some value C on the open interval from A to B. So that takes care of all the infinite points between A and B, But then in addition to that, we also have to have what about f of a? Okay, so at the left endpoint, how would we change that? Well, f of a exists, right? How are we going to write the limit this time? We're at the left endpoint. The limit of f of x as x approaches what? If I'm on the left endpoint, yeah, I can only approach from the right, can't I? If I'm at the left endpoint, the ant can only walk from the right. It can't walk from the left. There's no place to walk from. Function doesn't exist there, right? There's no solid ground for it. So instead of our regular two-sided limit, we'd say the limit of x as x approaches a from the right equals L. And then finally, these two things have to be equal. The limit of f of x as x approaches a from the right equals f of a, right? And I would do the same thing for the right endpoint also. Right, I'd have f of b exists. The limit of f of x as x approaches b from what direction? From the left equals, I'll call it L2, L sub 2, because it could be a different value, right? Should probably call that L1. And then finally, the limit of f of x as x approaches b from the left equals f of b, right? And so if I add, I have to have these extra restrictions on there to take care of that endpoint. What am I really trying to, you might think, well, why? Big deal. I mean, it's just we've got these endpoints. Can anybody think of a picture I could draw that if I didn't have these little contingencies written in there, this legal fine print, I could have a function that's truly not continuous on the closed interval, that actually is defined everywhere? How could I draw a function that's defined on some closed interval from a to b and is continuous on the open interval, but not at the endpoints? Anybody think of that? So here's what I'm talking about. So here's, let's call this A, and that's B. It's going to be continuous on the open interval, so everywhere between A and B, it's continuous. But it's not continuous at the endpoints. What could I do? Just to my graph. You have to write a function down. Any thoughts? Sure. Function exists on the entire interval, right? But I don't, anybody see where that falls apart? The limit from the right doesn't equal the value of the function at A, and the limit from the left doesn't equal the value of the function at B. So we do need that little addendum, right? Okay? All right. So this kind of summarizes what we just said. Function said to be continuous from the right at A if the limit of f of x as x approaches a from the right equals f of a. And it's continuous from the left if the limit of f of x as x approaches a from the left equals f of, hang on. Oh yeah, at a, we said b, but they're saying a, right? Yeah.
Will we ever deal with limits that involve complex numbers?
Well, I mean, you could do all this stuff with complex numbers, you're just dealing with different numbers. We won't. We won't, but you could just as easily do it.
I was
It's fine.
ju-
They're just, I mean, there's nothing special about complex numbers, they're just different numbers.
I was just thinking of it as, in the previous one with the house or car, I was thinking of it as having a limit outside of the defined one, just to take all complex numbers.
I'm not following that. I don't,
If it was less than -2 or greater than 2.
well, we'll talk about it later. I don't want, I mean, I'm not following what you're saying, but it's, I'll just say this, it's, complex numbers sound real difficult, just because they're complex numbers. They're complex, they must be hard, right? They're just numbers. I mean, there's a whole, if you go on and study math, you'll do a whole series of, like, I mean, you'll do complex analysis, which is just all the stuff we do. This is really analysis, real analysis, just with complex numbers. It's no art, it really isn't art. They're just use complex numbers that have imaginary parts also. But it doesn't really make the concepts any harder. Just weirder numbers that you're not used to dealing with. Okay, so that's repetitive. So here's what I really want to get to, though. Here's our first big ticket item in calculus. We get about 4 of these this year. Arguably 3, but we'll all say 4 of these big existence theorems that are extremely important. So these are they may not seem like they do a lot at first, but we get a lot of mileage out of these in calculus. So the first one's called the intermediate value theorem. Now the way these existence theorems work, I'll write that down. Is that if you meet a certain list of criteria, then the theorem guarantees the existence of something interesting. That's the way they work. They are frequently summarized best by a picture. Sometimes they call these picture theorems. Okay? Now think what this is saying. And the reason we spend so much time on continuity is because the intermediate value theorem depends on us understanding the concept of continuity. So let f be continuous over a closed bounded interval made of b. Was there a question?
Will this be online?
Oh, yeah, this will all be online. Yeah, everything's, I think it's totally up to date through last, whenever, Friday or something. I'll update it again today. Video and notes, both be up there. So f is some, we're going to call it a function. It's continuous on this closed bounded interval from a to b. If z is any real number between f of a and f of b. Now, I'm not saying a and b, I'm saying f of a and f of b. What's f of a? Okay, so it's the output of the function. Graphically, it would just be the y-coordinate, right, of the function at x equals a. So if that's true, if we have a function that's continuous on this interval, this closed interval, and if we've got some y value that's somewhere between f of a and f of b, right, then the intermediate value theorem guarantees that there is going to be at least one number c in the interior of this interval that satisfies f of c equals z. Okay? I kind of like the way that your regular textbook, in fact, I'm going to take a picture of it. I like it better. This one seems a little shoddy to me. I'm going to take a picture of this real quick and put it up here. Where is that thing? Oops. There we go. That's a little better. They say the same thing. This just seems like it's a little shorter. Okay, so once again, does that make sense? So we got some functions continuous on the closed interval where f of a is not equal to f of b, and they called it k, is any number between f of a and f of b. Then there's at least one number c on the interval from a to b where f of c has to equal k. That makes sense, doesn't it? Now just think about this. Let's just draw this graph. Now they're saying that f is continuous, so I can draw it without picking my pen off the board, right? So let's just say that this is a, and let's say that's f of a. There's the point with coordinates a, f of a. And let's say that this is b, and let's just say arbitrarily that that's f of b. So that's the point with coordinates b, f of b. I defy you to graph a function that's going to connect the blue and the red dots that doesn't go through, we'll call that k right there. K is just some value between f of a and f of b. I defy you to draw a continuous function that's going to somehow get from the blue to the red without passing through the orange. Can't do it, right? You'd have to pick your pen off the board, which would make it discontinuous, right? So if, all we got to do here is if the function's continuous on our interval, and if there is some value that's between f of a and f of b, that's all you need. You're guaranteed there's got to be at least one place where the function's going to pass through that horizontal line, pass through that value, right? No big deal. It's not like it's a super complicated thing. That's it, and the picture is very valuable, okay? So let's, and you know, there's another shot at the picture, right? They called it z instead of k, but oh well, same thing, right? There's got to be some intermediate value there that passes through that. So let's try this in a couple of math problems. How does this show up in a problem? Let's try this one. Oh, by the way, intermediate value theorem, here on out, we'll just call that IVT. Okay, for intermediate, we don't have to say the whole thing, just kind of wordy. So let's show that f of x equals x minus cosine x has at least one zero. How can we do that? Well, you could, but if I set it equal to, I mean, I could. But I don't want to do that. I just want to show that it does have one. And we could argue, without even having to write anything down, we could just talk our way through this pretty easily. All we have to do is meet those criteria. First of all, is f of x continuous? I mean, is there any place it's not continuous? No. It's continuous everywhere, isn't it? X is continuous by itself, and cosine x is continuous by itself. And so if I add those terms up, it's continuous, right? So we already met criterion 1. It's continuous everywhere, in any interval we choose. Is there at least some place where f of x is negative? Oh, just one point. Can we convince ourselves there's at least one point where it's negative, has its negative value? 0. Okay, so we could show that f of 0 equals 0 minus cosine of 0, which is 1. So it's negative 1. Okay. Is there at least one place where it's positive? 1. I'm going to make it totally obvious and say 10, because cosine's only going to oscillate between negative 1 and 1, and so for sure I don't need to figure out what it is. I know it's positive there, right? And so if that's true, some positive number. So here we know f of 0 is less than 0, f of 10 is greater than 0. So would you agree that 0 is a value between f of 0 and f of 10? Everybody agree? That's the proof. It meets the criteria for the intermediate value theorem. So it has to be true, right? Everybody see that? As long as we meet the criteria by the intermediate value theorem, there exists at least one place where that happens. Okay? How about this one? If f of x is continuous over the closed interval from 0 to 2, and f of 0 is greater than 0, and f of 2 is greater than 0, could we use the intermediate value theorem to conclude that f of x has no zeros? Does this really match with what we've been doing? It doesn't fit at all, does it? We can't make that conclusion. It's possible that's the case, but it's equally possible it's not the case. But more importantly, that doesn't even fit with the mean value theorem. So if it's continuous on this interval, the mean value theorem says that if there is some value of the function between f of 0 and f of 2, well, that's not what this is even getting at. All this is telling us that they're both bigger than 0, right? Does that mean that the function can never be negative? No, not at all. We could go back to a previous example, like this guy right here, right? So we know that, whoops, wrong color. We know that the function has to pass through this orange line, but does that, just because these are both positive values of the function, does it mean the function's never negative? No. Function could do crazy stuff. It could do that. It might go through the orange line many times, and it might be less than 0 in some places. The mean value theorem says nothing about any of that stuff, right? Okay? So no, doesn't say anything about that. How about this one? Let's try this guy. Can we show, for example, that this function has at least one 0 on that interval? Okay, so we could evaluate the function at -1 and get what for my answer? -1. We could evaluate it at +1. We get +1, right? So is this telling us then k is some value in between -1 and 1? Can I use this to justify that there must be at least one 0?
Yes.
We didn't follow the intermediate value theorem though, right? What are the criteria? Function has to be continuous on that interval. Is this function continuous on that interval?
No.
It's not. Doesn't apply. IVT doesn't apply. Okay? Make sense? And if we were to graph this thing, what we'd see is, in actuality, there are no zeros. That's what this looks like. Okay? How about this one? So let's just check off the boxes. 1. Whoops. For IVT, we need two things. We need continuity, and we need a value between f of a and f of b. So is this function continuous on this interval?
Yes.
It is, right? Where is it discontinuous? At 2, but 2 is not on this interval, so we don't care about it, right? On this interval, we're fine, okay? So, oops. Too excited. Too excited about math, I can't even take time to write. Check. It is continuous on that closed interval. Step 2. What is f of 5/2? Oh, and I want to know, by the way, I'm not even asking about 0 this time. I want to know, I'm going to switch it up on you. I want to ask, is there some place where Is there a place where the value of the function equals 11? What is f of 5/2? You can do it in a calculator, somebody. Just what is that gonna give us if we plug in 5 halves? So just put 5 divided by 2, store x, and then just put in that expression. Big number. What is it again? 55 over 2. Okay. What is f of 4? 16 plus 12 is 28 divided by 2, so 14. Is that, no, I did that wrong. Didn't I?
Yeah, 14.
14, oh, I guess I did do it right. So could we conclude that?
Yes.
Can we?
No,
Is 11 halfway between there? Is it between?
it's not.
We can't. What if I picked a different number? What if I picked a number like 15?
No.
Then we could.
Why?
Because 15 falls in between 55 halves and 14, right?
You're not wrong.
So then there would be guaranteed, there's going to be some place on this function where the value equals 15, right?
What?
Okay, we'll finish this up tomorrow. I kind of left you hanging a little bit.